minus d over 2, and then gamma 2. And then delta is just, sorry, this should be a minus. It's just alpha 1, alpha 2, k squared, and then 2 minus d over 2. And then we still have to do the alpha integral. Okay. Okay, so now comes a point that I want to make. So first of all, so you see that because we're keeping this in d dimension, because of course this quantum field theory, I could define it in any dimension I want. Right? I can just define it in any, this is just some scalar theory, I can just define it in any space-time dimension I want. 我们现在让这个 d 是自由的，因为我们 principle 我们这个 theory 是可以 define 在任何的 dimension。Good， 所以你们谁可以告诉我？我现在 claim 我 OK， 我现在 claim 说，光是写成这样子的时候，你们就已经可以看出来，它什么时候会发散，在 d 等于多少时候会发散。所以我要你们回答说，你的 critical dimension 是多少？从哪一个 dimension 开始，这个 theory 会发散？ So this is our final result. I'm claiming that from this result, you can already see that when d equals to particular values and upwards. So let's just assume that we're in the usual space time. So that means that d is an integer. Okay, so what is the dimension in which that integral starts to diverge? 谁可以跟我讲答案？我 claim 说我积成这个样子之后，你已经知道它什么时候会发散。是，为什么是？啊？还有谁有答案？需要提示吗？跟 gamma function 有关。The hint is gamma function. What is the special property of gamma? So when does gamma? So is gamma function always finite? You should have learned gamma function before, right? 你都学过 gamma function 吗？好，我们来玩这个。你们没有上过 gamma function 吗？以前应数课没有 gamma function。好，我们来认识一下 gamma function 好不好？谁现在可以告诉我 gamma function？OK， 我现在 ，sorry gamma c 啊，它的定义是什么？谁可以跟我讲？它有个积分定义。你们现在就有，你们谁有手机嘛？你进去可以 search 啊 ，Wikipedia gamma function。
From 0 to infinity.
From 0 to infinity, and
exponential minus t.
Exponential minus t
times t the powers of z minus 1.
Z minus 1
dt.
dt. Okay, so somebody told me that this is the definition of gamma function. Do you agree? 你们同意吗？以前有看过举手。OK， 大家都看过嘛，对不对？好，我们看这个东西，你们应该就能够看出它 OK， 它现在积分有上下两个线嘛，一个是无限大，一个是零嘛。在无限大的时候，它可能发散吗？只是单纯的一个数学的，无限大的时候可能发散吗？可能 diverge when t equals infinity， 有可能发散吗？这是很重要的事情，不可能嘛。 对不对？因为它在无限大，就算你 t， 你先不知道它这个 z 的倍数是这个 z 是多值是多少，可是不论怎么样子，它到无限大的时候，它都是 polynomial 的增大，它是很像一个 exponential suppressing factor 嘛，对不对？任何时候，如果说你有东西是 polynomial 的成长，你再乘上 exponential decreasing factor， 谁赢？exponential decreasing factor 赢嘛，对不对？所以你 obviously 知道这个东西在 z 是任何值在无限大的时候是你不用担心它会有发散。所以你在下要担心发散是不是？所以任何的积分你要看它有没有发散，是先看它的积分上下限嘛。上限没问题，你再就看下限嘛，对不对？你再看它下限的时候，因为 t 等于0的时候，这只是1嘛，对不对？所以这时候你就看到它下限的时候，它会不会发散？会不会？会嘛，对不对？从什么时候开始发散 ？z 等于什么时候开始发散？是不是 ？in principle 从 z 等于0就开始发散 ，z 等于0 ，z 等于-1、-2、-3，是不是都会发散？对不对？大家同意吗？对不对？所以说 gamma function 会有 pole， 在 z 等于0、-1、-2、-3的时候会有 divergence。OK， 这是你们应该要学过的。OK， 你们那时候在学 gamma function， 你们应该学过 gamma function 是 analytic function and the whole complex z plane， 只有 single pole 在0、1跟负的 integer 的地方。OK， 大家可以接受吗 ？OK，good。好，所以你们知道 gamma function， 所以我现在回来问你们这个问题，这个东西在几维的时候会发散？在几维？4维，对不对？因为4维是不是这个 gamma function 开始出现了？4维以上的时候，这个 gamma function 是不是会一直不断的那个发散？对不对？一样4维，对不对 ？Good. So since the gamma function has pole singularities at 0 and negative integers. So that means when d equals 4 is actually when this integral starts to diverge. Okay. So that means the critical dimension of this theory, in order for this to be finite, the critical dimension is actually d equals 4. We'll come up with this very often. So basically, let me just give you a preview, a statement, and that is for any theory to be renormalizable. It's just a statement, and we'll understand it more and more as we go along. For any theory to be renormalizable, that means that the critical dimension has to be d equals 4. Okay, if something is d beyond 4, if the critical dimension of the integral is d beyond 4, that theory is not renormalizable. Okay, but this is just introduce the notion of what is the critical dimension. The critical dimension is when this integral starts to diverge. Okay, good. Now, we still have to do our work. So, now we have a problem, right? Because if we stick in d equals 4 here, this is just going to be an infinity. Right? We're just going to have an infinite, and we don't know what to do with that, right? But you know, precisely because you have a critical, because that the gamma functions has poles at integer, a 0 and negative integer. That means that it has only single poles. So in mathematics, when a function has only single poles, and perhaps just branch cuts, you get analytic continue your value, right? 我们常在说，你们任何时候你们在学复变的时候，你们都学过，如果你的复变函数只有 single pole 的话，或者你有 branch cut， 你可以 define 它的 analytic continuation away from 这个 pole 嘛，对不对？那所以说，既然这个东西是有 single pole， 那所以我们就 define 这个 computation， 它的 divergence， 我们就 analytic continue d away from 4 dimension。OK， 所以换言之，我们要引入我刚刚讲的，我们上次讲的 dimensional regularization。OK， 是什么呢？就是我让 d 等于4减 2 epsilon。Okay, we're going to try to regularize this integral. By regularizing, what I mean is that since this integral is giving you something that is infinity, but we cannot just play around with infinity. We cannot do any manipulations with it. So what we want to do is we want to take this integral, separate a piece which is infinity but is well defined, and then contain some piece that is finite. Okay, so regularization means that we're separating the something that is infinity to a piece which has a well-defined infinity and a piece that is finite. 这是 regularization 的意思。Okay， 我们现在是要 define 我们 integral， such that 我可以 control 我的 infinity 在哪里。OK， 那我 control 的方式，因为我们刚刚是不是知道你的 critical dimension 是4维嘛，对不对？那时候就让它稍微小一点，这样稍微的 below 4维哦，是 below critical dimension 嘛，对不对？我应该可以看出它是 finite 的，对不对？所以我就 define 我的 d 是4减2 epsilon。所以这个是就是我们所谓的 dimensional regularization 哦，上次有提到，这是一种 regulator 的方法。那它的好处是它 UV 跟 IR divergence 都可以regulate 它。OK， 那我们现在看到这个积分是 UV divergence 还是 IR divergence？ 你们觉得？认为是 UV 的举手，我认为是 IR 的举手。OK， 好，这是 UV divergence。OK， 因为很简单，为什么它是 UV divergence？ 因为我现在这个 integral 已经擦掉了，原来的 integral 是 dl， 我们现在是4维，我们 divergence 在4维。在 L 趋近无限大的时候，这 integral 是 behave as dl 4次方 over L 4次方。对，在 L 很大的时候嘛，对不对？所以这个积分是不是？是 logarithmic 发散，我们上堂课有讲，对不对？所以这有个 UV divergence。那如果说是很小的时候 ，L 趋近于0的时候呢，这 integral 是什么？是不是 dl 4次方？这边还是 L 平方，可是这边因为 L 趋近于0了，所以说最大的项是 K 平方，对不对 ？K 是 external momentum，K 是外面的这个 P1、P3 加 P4。对不对？那这个东西是不会发散，在 L 等于0的附近并不会发散，对不对？因为所以这边有个这边有个 L 平方，可这边上面会有个 L 3次方的去跟它 cancel， 它上是 regular 在 L 的。OK， 所以代表说你这边如果算出任何的发散的话，它是一个 UV 的发散，它并不是 infrared 的发散。OK， so this divergence is an ultraviolet divergence. It's not an infrared because you can just look at this integral. You can look at this integral, and you see that if you look at the region where the L is extremely large, it becomes dl to the 4th over L to the 4th, and this is you see that you have a logarithmic divergence. But if you look at the region when L is near 0, you have L squared, but then when L is near 0, you don't see L here, you only see K. This is just K squared, so then it becomes dl 4th over L squared. And near L equals 0, this is actually perfectly finite. This doesn't diverge near L equals 0. Okay, even though there's a 0 here, but there's more powers of zeros upstairs. Okay, so this is infrared finite, and this is a UV divergence. Any problem? Any questions? There's another physical way to understand why this is an ultraviolet divergence. Let's just look at this graph again. Now, if you remember last time when I was talking to you, telling you about UV divergence and infrared divergence, do you remember that I said infrared divergence only occurs when you have massless particle coming in? Remember? 对，我们说为什么会有 infrared divergence？ 我们是说因为你有 massless particle 嘛，对，你有没有质量的 particle？ 那你有没有质量的 particle 的时候，你的 S matrix 是 ill-defined 的嘛？我们上次有讨论到说这样，因为你不能区分一个光子跟两个光子之间的差别嘛，对不对？好，那我们先来看这个问题，你会说，哎，这个不是 massless particle 吗？那为什么它不会有 infrared divergence？ 那原因很简单，因为重点是我们在看这个图，你今天画这个图的时候，你说哦，我先有2个 particle 进来，2个 particle 出去，我们画这个图的时候，我们会这样子讲。但是我们写下我们的 integral 的时候，我们是写下什么东西？我们 integral 本身是不是只是写成 dl 4次方分之 L square L 减 K 平方？对，我们刚刚一开始是不是写下是这个样子？从 integral 它本身的角度来讲，从这个家伙它本身的角度来讲，它分不出来它没有看到2个 momentum， 它只看到1个 momentum K 进来。那这个 K 是 massless 还是 massive？K 平方会等于0吗？ k 平方会等于0吗？认为它会等于0的举手。认为它不会等于0的举手。OK，very good， 它没道理等于它是两个，虽然 k 等于 p1 P3加 P4 ，P3 平方加 P3 平方是0，P4 平方是0，可是 P3 加 P4的平方并不一定是0嘛，它会 depend on P3 大 P4嘛，对不对？所以这个 k 实际上是个 massive 的 momentum， 所以对这个 integral 来讲，它实际上是个 massive momentum 在进来，所以它 effectively 等于在 compute something in a massive theory 一样。OK， 所以它不会有 infrared divergence， 这样大家可以接受吗？我刚刚第一个讲法是我仔细去分析我的 integral， 我会看得出来它为什么它是 infrared divergence 而不是 UV divergence。另外一种讲法，我可以从 integral 本身的角度来讲，你今天可以画这个图，对，我今天画成这个样子，我今天也可以把它画成这样子，把这个 momentum 把它拆分成好几份，但是对 integral 本身它只是在算这个东西，对不对？所以它只是总而言之，它就是看到一个 massive 的 momentum 进来。然后你知道你的 integrate 出来的结果，所以它当然不可能会看到什么 IR divergence， 它 effectively 等于是在看 massive 的东西进来嘛。这是为什么它没有 infrared divergence。OK， 所以这是另外一个很重要的一个 point， 就是你们在画，我们常常都想说，我们在画一个图，然后这图就代表什么意思？但是实际上你在做运算的时候，比如说这个里面，你知道这是 P1 加 P2， 这边是 P3 加 P4， 但是你真的在算的时候，它根本不 care 你的外面是 P1 P2 P3。它只 care 是它 physically feel 的 momentum flow 是什么东西，对它 OK， 所以这个你们慢慢会碰到一些陷阱，就是你觉得你们画这，你们会觉得好像能够区分出来，但其实你 integral 根本看不出来，说是你到底有几个 momentum 进来，这个我们到时候会碰到。Alright, good. So we're going to use dimension regression. We're going to set d equals 4 minus 2 epsilon. So if I stick it into here, then this just becomes, again, I lambda squared. Now this is going to be gamma epsilon. Okay, and then this is 4 pi squared. D over, this is going to be 2 plus, 2 minus epsilon. And let me just keep everything, all the epsilon factors here. And then this is just going to be integrate d alpha 1, d alpha 2, delta 1 minus alpha 1 minus alpha 2. And then alpha 1, alpha 2, k squared minus epsilon. Sorry, plus epsilon. Okay? Now, finally, even though this is completely useless in this integral, I'm just going to give you one final. So we're going to use 3 different identities. The first identity was the Feynman parametrization, which allowed us to write all the propagators in the same denominator. The second identity is just a trivial thing, which is a spherical loop integral identity. Well, not identity, just giving you the result of the integral. Okay. And the third identity is the final Feynman parametrization integral. And so again, this you can also prove it very straightforwardly, but let me just integrate the general form. So the general form is that if you have something that is integrating d alpha 1 all the way to integrate d alpha n, this is all 0 to 1, 0 to 1, subject to that 1 minus I equals 1 to n, alpha n. And then I'm integrating, let's say alpha 1 to the mu 1 power, alpha 2 to the mu 2 power, all the way to alpha n to the mu n power. And this integral is equal to gamma b1 plus 1, gamma b2 plus 2 of 1, right, gamma vn plus 1 over gamma n plus sum of I 1 to n vn. Okay? So I'm just going to leave the proof of this to you. This is a very simple. You can also do it as a recursive proof or whichever way you want to do it. It's also just give you the result. But anyway, we don't actually need to do this right now because this we already know that this is actually relatively simple integral. So we have gamma epsilon. So this is a divergence. So we can expand our gamma function around epsilon equals 0. So gamma epsilon is equal to 1 over epsilon minus, let me just call this gamma, and then plus order epsilon plus order epsilon. Okay, so you see that when epsilon is equal to 0, there's a divergence here, right? You see that, right? When epsilon equals 0, there's a divergence piece here. Now, but you see what we're doing, because we're doing analytic continuation. So now we can separate away this divergence piece, and then retain all the finite pieces. Right. So this is what regularization does. It allows you to analytically separate a divergence piece and maintain the remaining finite pieces. So this is the Euler gamma constant, and this is just defined as the derivative of gamma function evaluated at 1. Okay, just take the gamma functions. I mean, the gamma function has an integral representation, right? You can take the derivative and you just evaluate that derivative at 1. This is just a numerical number. Let me see what I can, actually I copied it down. So this is just 0.57721. Okay, this is just a numerical number. The reason that you have this gamma derivative is very simple, right? Because what do you use? You use identity that gamma 1 plus epsilon is equal to epsilon gamma epsilon. Right, this is identity. So you can prove this identity. Okay, so then all you want to do is expand this gamma function when epsilon is near 0. Right, and so that means that you're taking gamma 1, which is just 1, and then plus the derivative of gamma evaluated at 1. So that's the subleading term, which is this piece, which is why it's defined as the derivative of gamma function evaluated at 1. OK， 这只是个泰勒展开。你们知道有这个伽马方面有这个递回的关系吗？对不对？伽马 n 加1等于 n 乘以伽马 n 嘛。对，所以这个我只是在用这个递回关系。OK， 然后所以就代表说。伽马 epsilon 等于 epsilon 分之1加这个，就是说你们 just in case 你不知道我在说什么，这代表伽马 epsilon 等于 epsilon 分之伽马1加 epsilon， 这时候我就可以做泰勒展开了，就是 epsilon 分之伽马1再加伽马 prime 1嘛，对不对？这一是 derivative 嘛，所以这是为什么这个？我这样好像讲太多话。Anyway, so that's what it is. Okay, good. Now we're down to business. We see that we're finally at the end, and we see that, let me just write this down so that I don't make any wrong signs. So we see that after putting everything together, so this is just 2, so this is 16 pi squared. So the final answer is that this contribution is actually lambda squared 16 pi squared multiplied by 1 over epsilon. So this is the leading piece. Now let's see. So there's a 1 over epsilon. Now we need to take the finite piece. Now of course there's the 1 over epsilon plus the Euler gamma thing. But then what else is a finite piece? There's other pieces that are finite that comes from, for example, this epsilon that you expand from Taylor expansion, right? And this thing will mix with the 1 over epsilon coming here, giving you something finite. So this will give you some other constant. These are constant terms, which comes from expanding this, and perhaps expanding some of these finite integrals. But the important thing is that this also has a k squared to the epsilon, right? So this actually has an additional term, which is minus log k squared. So let me just stop here for a second. 你们都可以看到这个为什么会有这个？你们都看到这个 log k squared 的来源吗？因为这是不是有个 k squared 的 epsilon 次方，对不对？所以你的 k squared 的 epsilon 次方是不是等于 exponential epsilon log k squared， 对不对？这是 identity 对。 然后这时候是不是见 epsilon 很小，是不是可以做级数展开？所以在 epsilon order 的时候，这时候这个 epsilon 是不是就可以跟这个 one over 它前面乘上的这个 gamma function 的这个 one over epsilon cancel 掉，得到一个 finite 的 piece， 对不对？但是因为 k square 在分母，所以这上是负的，所以这边是负的，所以这是为什么它前面有个负号。OK。All right. So here we have this log k squared. Okay, so this is our final. Then there's some irrelevant constant. You can also call this order gamma irrelevant constant, but these are just constant pieces. And then all the higher order are just epsilon order pieces. Okay, so this is the final result of this integral. Okay, so now we're going to just talk about the physics of this answer. Okay. But this is just the result of just integrating your quantum correction. Now, first of all, as always, as any good student, whenever you see a k squared in a log, you're not happy, right? Because whatever is in the log cannot have dimension. 对不对？这 log 里面的东西不能有量纲嘛，对不对？所以任何时候你们看到这 k square 是 momentum square 嘛，对不对？所以说这是有量纲的。所以代表什么东西？代表说你会希望在下面放下一个带有量纲的东西。那你会说这个东西，问说我怎么知道这东西从哪里来？我你也知道这个东西会有一堆的 constant 在这边嘛，对不对？你永远都可以 add 一个 constant 让它变成没有量纲，对不对？但是当然你会说。所以我首先第一件事情是 ，OK， 第一件事情是我 claim 说我可以加一个这个 piece 在这边，让它没有量纲，让它这个里面的东西是没有量纲。可是这意味着什么东西？这意味着说你是必须要引入一个有量纲的东西，对吧？我们现在还没讲这个 lambda 是什么，可是这是意味着你需要引入一个有量纲的东西，对不对？所以说，先把这个，所以我们再算是我现在图应该可以擦掉，因为。所以我们应该不要往上面，等于负 lambda I， 再加上我们先看的 lambda square 16 I square 1 over epsilon。我现在 constant piece 我都不管它了，减掉 log k square。分子的上面。确定一下我们正负号是对的。我们要弄这个。所以我想想看。Okay, let me just erase this factor. 好，我先做一下说明。由于我刚跳了几步，所以这 I 的 factor 有点 off。所以我先说明，你们这个可以看shorts， 这个部分它的积分并不是用我这样的方式积的，但是因为我是要给你们说你们之后都能够任何的积分都能积，这个我是比较复杂一点的方式积，因为他只是想要抓 log 的 piece， 所以它积分比较简单，但是重点是它的那个 I 的 factor 就沿用它的好了。所以我看一下是，我先跟你们讲在哪里。所以15.4.1就15.4。这个部分 ，OK， 你的每个 order 的这个 I 的 factor， 我们就跟着它的这个15.4跟15.4.1 ，OK， 你们就跟它的 I 的 factor， 我就在这边我不回去，不浪费时间回去追溯这个 I 的 factor，OK， 对，所以这边会有加个什么 ，OK， 所以这是我们积分出来的结果。当然，by the way， 它的那个。